Good evening, everyone. Codes after the difference between filter and wrapper. I said probably we can hold on to those codes, right? Because I have actually changed a little bit of track. We are going to look at so you can actually focus only until that understanding of the because here I think I have jumped a little bit more quicker by bringing in the different algorithms. So once we discuss about the various algorithms, possibly the applications wise, we can think of how this algorithms can really help us in terms of feature selection. Possibly that is something that we can do. That's the reason I have possibly you just hold on once we discuss about the random forest and a few other algorithms, we can jump in into that activity. All right. So, so what I was thinking of is possibly a kind of a ready-made solution, right? So wherever you have to address a classification problem, right? To a large extent, what all activities need to be done right from the beginning. So possibly the better way to address this is take this data or take this piece of code and try to take a different data set and try to work out more or less in lines with this data with this code and see to what extent the rework is necessary from your side. So we are trying to look at in such a way that almost all the tasks that we have looked at, I can think of incorporating into this, right? So that is what is this case study talking of. So all the algorithms, all the machine learning algorithms relating to the classification, at least a decent set of machine learning algorithm, we are going to look at in this. So whenever we are starting, these are some of the basic libraries that we will be loading, right? Then at the beginning itself set the display maximum columns and rows. Then I can very well get the input file. So either I can get it from the Google Drive or I can get it from my file system. So if I want to get it from the file system, I'll simply say import files. Otherwise, if you want to get it from the Google Drive, import drive. Right? And then you say drive.mount there, and here you will say uploaded is file.upload. So whatever is the name of the file, you will upload it and then you will read it. So I have created that lone default data only, which was having 1,48,000 records or something. Now I have made it as a mini, saying only 5,000 records are there, because that would help us in executing the model much better. I don't mind even making it 1,000 record because it can execute the model much more faster. But nevertheless, I have kept for 5,000 records. So I am reading this data. Then there are some preliminary checks, applying some of our functions, finding out the length, finding out the shape. I hope we are all comfortable with all these. Looking at the head just to see what are the typical patterns. Looking at the tail, identifying how many records are there, because you will get the ID numbers, and you are just ensuring that the typical data is loaded as per your expectation. So apart from the first few and the last few, you can even think of sampling randomly also. This is also just to check what is the typical pattern of the data. Yeah, loan default is different from loan mini. The same data, but I have taken only a subset as 5,000 records. I'll share that data set with you. If you want it right now itself, I can share it. If you are fine at the end of the class, I can share it at the end of the class as such. Okay. Then so the next thing, columns. Look at all the columns. See if all the column names are in line with the typical naming convention. If at all any of them is violating, rename the columns. And if at all something is too long, something is not that clear, just rename the columns. The most common thing that I do as a part of renaming, so this is the code for renaming the column. So it's a kind of a dictionary format, key value pair. Status is whether the status loan has been defaulted or non-defaulted. So what we are saying is always change that word to target. So this is just a practice. It does not hamper anything, right? Similarly, you can have spaces in the column name, not a problem. But when you are trying to work out, at some places, you will have a problem. You will have to use double quotes. You will have to use quotes in some places, or some of the operators you will have a difficulty in using. So it's always better to put an underscore. That's a very common convention in the column name. But you can very well have space. It will not give you an error, right? But typically, sometimes the readability also will become difficult when you are sharing something with someone. Possibly the readability also, in terms of people start thinking that they are two different variables suddenly. So that way you will have some kind of problem. So better try to put a kind of an underscore and bring a lot of clarity. So here I'm just replacing it with something so that if at all there are some renamings that I need to do, I can do it in this way. Right? Then similarly, I can talk about co-applicant credit type. I have changed it to co also. I have put an underscore rather than a hyphen. So because that's a kind of a common convention that we typically follow. And by saying in place equal to true, you are replacing it, overwriting it, right? So that is what is happening. So initially you got the data, you looked at the columns. If at all some kind of renaming is required, you will do that. Then you look at the info. Info has two major objectives. One is the missing values. You can very well see which columns are having how many missing values. And the second thing is the data type. Two major things that you will infer, apart from getting the list of all the columns that you have in your data. So for each of the data, how many missing and how many of each data type are there? What is the data type of each one of them? So the objective is, if at all any of them is not following the data type as per our expectation, possibly you have to keep looking at them. ID is an integer, loan year is an integer, and so on. So if at all you are finding that something is not, right, loan rate of interest is showing as a float, which is like a decimal, right? Loan amount is showing as an integer because it is not taking any decimal. But if you say you want it to be a decimal, because at some point I may have even the loans in terms of decimals also. Our credit score right now is showing like an integer, but let's say it might be in this data it might be showing as an integer. But if I say that it might be something else, it might be a float as well. Simply you can very well write it like this. So you can very well change. You can change the credit score. You can very well change the credit score as type float 64. So these are all like 64-bit numbers. So I can very well change like this. So the target right now it is showing as an integer. So I am converting it into an object because probably I may be interested in doing a kind of a classification problem. So I want to treat it as a category rather than as a numerical value. If it is a numerical value, then the problem would become a regression problem. So I may want to convert it into an object. So this is the kind of a pattern which you would be following in case you want to change the data type. So by observing the data, we are seeing if any data types have been wrongly mentioned. In that case, better correct them. This is a project. So I'm trying to put all the steps that are possible and whatever we have done till now. And from there, we will move on directly into the modeling using the various algorithms. Then you would do a describe, right? Descriptive statistics for the numerical. Major objective, identify if there are any unique observations in any column, which means the standard deviation will be 0 for that column, or try to look at if there are any wrong data entries altogether in the data. So probably look at the minimums and the maximums and see if all the values are in the acceptable range or not. If they are not in the acceptable range, those are the things that you can directly correct. Let's say if the interest rate, the minimum is, okay, interest rate spread or upfront charges. I'm just putting some. So it's a 0. Or probably income. The minimum is 0. So if I say no, minimum zeros are not possible, at least we need to have some income, then probably you are trying to make those values, replace them with something else. So that is what you are trying to identify, erroneous values or even some kind of erroneous values or some non-acceptable values or some kind of columns with almost a unique value in the entire column. Same goes with your categorical variables also. So this is what you are doing as a descriptive statistics for your categorical variables also. Here also the focus is on unique number of observations. So that if there is any column with only one unique observation, then probably you are going to delete that particular column as it will not add any kind of a value for us. The second thing also is the frequency, especially if there are two columns, only two categories, we will be seeing what is the ratio of the highest to the lowest, which means there are only two categories. So if the category, if one of the categories is significantly, now here you see 4,988 are belonging to one category only, and only 12 will belong to the another category. So when there are very few elements belonging to one category, then probably it would be better to eliminate that column altogether. Though we may say that category could be a very critical category and all, but the 12 as a number may not be sufficient to establish that as well. So unless I get some more additional information, it may not be a good thing to include those kind of categories in the model. So we'll see what all we have done accordingly. Okay, age is an object in this because it is like a age group, right? So that's the reason it was treated as an object. Probably when you look at the data, you would find that, right? So somewhere if you scroll through the data, you'll find that this is what is there in age 65 to 74, 45 to 54, and so on. Right? So this is the steps possibly. Then I'm looking at how many columns are having unique values. So you see that the loan year is having only one unique value. There are some more. Construction type is having only one unique value. Secured by is having only one unique value, right? And even the security type is having only one unique value, right? So what is that? We can very well try to get those columns which are having only one unique value. So those are the ones that are outrightly that need to be removed from the data set because they don't add any extra value. On the top of that, you can also look at the skewness and the kurtosis because this will help you to assess whether the variables are normally distributed or way away from normally distributed. Because if they are way away from normal, then two things. One, I can do a kind of transformations like logarithm, square root, something where the skewness is very high. I can do some kind of an activity where I can try to reduce the range of that data so that the skewness can come down. Wherever the skewness is negative, I can try to increase the range of the data where the skewness can increase. So looking at the skewness and the kurtosis, we can do some kind of non-linear transformation, non-linear mathematical transformations can be performed on the top of the data. So we could clearly see that almost every variable, with some exceptions like rate of interest, interest rate spread, some of the variables are highly skewed positively. The term is negatively skewed. These are positively skewed. Probably credit score is the one that is more symmetric with a skewness of close to 0. And target is anyhow a binary variable. So we don't need to bother much about it. Then we can also see the kurtosis values also accordingly. These are also talking about the peakedness of the data. So which means there could be some tails, extreme values in the tails. So I could see that there are some extreme values in the tails per loan year, loan amount, upfront charges, property value, income. So I could see that they are very highly chaotic kind of thing, which means there is a possibility of some extreme outliers in the data. So if required, we may want to identify the outliers and we may want to even delete those outliers also. So this is one more analysis that we may want to do. Then, okay, this is the detailed descriptive statistics. They are talking about the normality of the data and all as well. We could see that as per the Jark-Bera test, none of them are coming closer to normal. Right? Strictly, if I go with the definition of the normality, I'm not seeing any variable that is coming close to normal, which means either if I have to use some kind of linear models, like in this case, if I want to use a logistic regression or linear discriminant analysis kind of models, which are based on which assume the linearity of the data, more of parametric models, which assume a kind of a linearity in the relationships. In those cases, it is always better that you perform a non-linear mathematical transformation on the data, convert it to get more closer to normality, and after that you try fitting your models. So that is one thing which we can look at. Skewness and kurtosis are also typically derived in this expression itself. Now we are moving more into categorical variables, but this is what we have done for numerical. Descriptive statistics is typically a more detailed descriptive statistics is done for the numerical variables to understand what is the level of normality associated with the data. Then I can also look at the categorical. I can very well split the data into categorical columns and numerical columns. So wherever I'm seeing the data type is object, I'll get those columns as categorical column. Wherever it does not come as object, which means either it is integer or float kind of a data type, then we are associating them to numerical column. Then the next step that we are doing is frequency of each of the categories. In the categorical columns, probably even if you don't, if you have the same code, even if you don't have any categorical column, then also it will not show any kind of an error. So you can simply talk about these are the categorical columns and these are the numerical columns. For each of the categorical column, try looking at what is the frequency of each of the categories. So as long as the frequency is much lesser for one of the categories, if the frequency is much lesser, you can, and if there are only two categories, then it is better that you omit that column altogether. So for a 5,000, probably we can always go with, right? You can always talk about a minimum of some 30, or you can also talk about as 0.1% of the total data at least. Right? It's not the minimum of, I think, maximum of 30 or 0.1% of the total data. Even if I don't have 0.1% of the data also for one category, then it would have a kind of a problem in terms of analyzing such a huge data set, right? And that is not too much of an ask as well. So if I'm talking about 5,000 observations, 1% is 50, 0.1% is 5 observations. So I am talking about a maximum of 30,5. Especially if your data set is, let's say, 50,000, then probably we are saying that let that category be at least 50 observations, right? Because what happens is otherwise there could be a lot of biasing that comes from the existing category, which is a very dominant category. So I mean, in a dependent variable or in a target variable, if I have such kind of a difference, that's a different story. But in the feature variables, if such a kind of difference is there, then probably you can very well say that at least the minimum occurrence one should be at least 0.1% of the occurrences. Otherwise, probably we can drop on that category. So here you can very well talk about 30. Now I could see this construction type. There is only one category, so better drop it. Now here also we have secured by, there is only one category, drop it. Now this is where the hashing can come into picture, right? So there are two categories, 3U and 4U. All right, 3U and 4U. Probably you can very well combine the 3U and 4U. Either you can drop these two categories, or you can very well combine the 3U and 4U into something called others, right? And because at least if I add them up, they are coming up to 26, which is not a bad count, right? Probably if they are individually, then it looks like 14 and 12. So this is where the hashing can come up, right? When you are doing this exercise, you can very well plan on the hashing. So this is the credit type. I mean, I did not implement that, but now I got an idea. Why not we put that hashing here? Also 2U because it is less than 50. But again, I said the data is only 5,000, right? So 0.1% is just around 5. So I can say it as a maximum of 30,5. So if there is 30, I'm still fine with it. Otherwise, yeah, you can try that also. There's nothing, right? I'm just taking my version and I'm giving you where all you can still modify around it. it, because these are all like customizable solution, right? Everyone has their own understanding of the data, and based on that, they will have a different workout on the data. So then all these are looking fine. Here also, this one is also fine, 36. So I'll leave it like that. This one is also 40. I'll leave it like that. Whereas this one is all 5,000. So I'll drop the column and so on. So here I want to do that hashing. So I'll do this hashing. So I'll make both of them. So what is that I'm saying? I'll look at, I'm just bringing in the example of hashing also here, right? I'll look at this category. Where was that? Yeah, this one, total units. So what is that I'm saying? I'll take the total units, wherein the total units is equal to what is that 3u is equal to 3u, or this 4u, right? So when this is equal to either 3u or 4u, I would like to make it as another constant where I will say more than 2u, or probably will put greater than 2u. Greater than 2u. So this is where I'm getting into a hashing exercise. Let me just see. I think R is not taking. Okay, this is working. So we'll do it like this. Possibly there is a way out. So I'll have to look out for that. See, at the end, meeting the objective is important. So when I do these two things, now if I redo this summary once again, just to ensure that I have done it correctly. Okay, it might have got omitted. Okay, I have to run it again because anything less than 30 I have omitted in the next line of code. That's the reason I think 3 and 4 would have directly got omitted altogether. So because I am running the whole code, so they would have already got omitted. So I'll run it line by line so that we can demonstrate them wherever required. Okay, it's just a 5,000 records data set. So I'm reading this data set. Preliminary checks done. Okay, right now it looks like these are 4U, 3U. Now I have done this hashing. Okay, so now again, if I repeat this process, it looks like we have a greater than 2U and we have taken it as 26, right? So just not to lose out on that. So basically that is where the hashing can come into picture. Then we can also put some kind of error replacements. So if I say the interest rates cannot be negative, right? Rate of interest, obviously we don't have it negative in the data, right? But if at all I have some such kind of, by looking at the minimums and the maximums, if something is not in the acceptable kind of a range, right? So that is where I have put some kind of a code saying, if the interest rate is negative, make it as missing value. If the income is less than, so here I'm okay, rate of interest, even zero rate of interest, I'm putting it like a non-acceptable. Rate of interest of 0% also, less than or equal to 0. But I think in the data we had some zeros. So just for the sake of some discussion, I'm putting it. The interest rate, no, the minimum is only 2.75% here. So not to be worried about. So I am saying if it is less than or equal to 0, then probably make it as 0. Similarly, the income also, if it is less than or equal to 0, make it as a missing value. So that's how we are converting some of them into missing values, right? So, or you can try to, so initially we can make them as missing values, right? This is what in this code I'm trying to do. So whichever are the columns that you are finding it erroneous, you can very well try to replace them with missing values. So this is the piece of code that you can write for that. Then you can very well put a cap on the number of occurrences for each category, just not to lose out on that greater than 2U. I'll set it to 25 because our greater than 2U we got 26. So I'm just setting that any category with less than 25 occurrences, I'll replace all of them with blanks. Means I am trying to eliminate that category from my model. So I am replacing all of them with the blank values. So wherever, so if you see here, I'm taking for each variable. So this is a kind of a sophisticated way where we are looping across, right? That's what I have done here. I'm taking all the categorical columns because we have already segregated into categorical and numerical. I'm taking the column. So bank variable is what is, I'm taking that column. I'm taking the value counts of that column, which means all the categories and the counts, right? That is what I am taking. Wherein the rule that I am putting is that value counts is less than 25. Wherever that value counts is less than 25 and take their index value. That is, those are the ones which are becoming insufficient value. Now, wherever the index is in that insufficient values, corresponding to that index, we are replacing it with a blank. Okay, Winsorization is nothing but you are setting it to a minimum or a maximum. You are putting a kind of a cap. So Winsorization is nothing but you are adjusting it to the minimum or the maximum value. So any interest rate less than 0, make it as 0. Any interest rate more than 10%, make it as 10%. So that is what we typically call as capping right? Or sometimes in terms of some percentage also we talk about the Winsorization, like the lowest 0.5% of the data, cap it to the 5th percentile, or any data that is greater than 99.5 percentile, cap it to the 99.5 percentile, and so on. Right? So right now I'm not doing any of them. Right now I'm saying all of them will become blank, missing values. So any of these erroneous values, they are going to be replaced with blank. Similarly, any category with less than 25 observations, that would also be replaced with a blank. So this is the kind of a sequence that I typically follow. Of course, we can very well have some differences depending on the type of the project, but this is something that I generally follow any kind of task that comes to me. So this has been like over a period, this has got matured, and sometimes it keeps changing also, right? So this is a kind of a process that I generally follow. Then we are going to look at how many missing values are there for each. For each column, look at the missing value. Now I could clearly see that some of these columns, they have a large proportion of missing values. They are more than almost 25% of the values are missing, because our data is around 5,000 records. So in all these cases, almost 1300, 1200, 1300 is missing, which means almost 25% of the data is missing. So there are two ways of understanding it. So as we have already discussed, either I can think of dropping the columns altogether, right? Because a lot of, otherwise if I drop the rows, then a lot of data loss is going to occur, right? So in some cases, if such a large number of missing values are there, and I'm losing out a large portion of my data, then it would be better to drop the column. You may always argue that this column could be an important column, etc. But if it is not present in almost 25% of the data, then it may not be a good column to work. Now here, yeah, I think I have talked about the Winsorization. Okay. So that is where I can even think of dropping the columns here, right? In these cases, I don't know. Probably we may want to drop the rows, unless you have a specific understanding of why these values are missing. In some cases, there could be a business logic for missing, right? Whereas in some cases, it could be just that the data could not be collected, right? So these are the columns which are having some kind of missing values. So some of them I have done something. Like let's say, okay, you want to delete a column. I'm deleting some columns here, especially these top three. I'm deleting these three columns because there are more than 25% of the observations are missing. You can very well say probably you create a second model where you don't delete those columns, but probably delete those rows, right? There is nothing that will stop you from doing that. So in this scenario, I'm dropping these three columns, and along with that, I'm dropping some other columns also, like ID, because ID does not add any value. Low near, because it is having a one unique, it is having only one unique value for the entire column. Construction type, we have already seen that there is only one unique value. Secured by and security type. So these are all are having only one unique value for the entire column. So I'm simply dropping all those columns from my analysis. Now, probably you could very well say, why not you drop the others also? DTIR, LTV, where there are almost 800, 500 kind of missing values. right? Probably that's also something that can. But if there are hardly 5% or 10% of the observations that are being lost, you can very well think of removing the rows rather than trying to remove the columns from the data. And in some cases, I just wanted to showcase. So if at all I want to do some kind of a Winsorization, that is what people were asking. So if at all there is a missing, I've just taken it for the term. So there are 4 missing values for the term. So what is that I am saying? Replace it with the minimum most value. So whichever, so it may be wrong, but I'm just giving you some, I mean, in case you want to do this in your code, you can do it. Minimum, maximum, mean. So I've just taken one function, right? Filling it with some kind of a function. Or in some cases, I have just hidden it out. So it can very well be, I can fill it with some kind of a blank value, some kind of a constant value. Let's say loan to value ratio, right? Here, so where is my loan to value ratio? There are some 545 missing values, right? So sometimes I may think of filling it with some constant. If at all loan to value ratio is not specified, take it as 100%. I don't know whether it is right or wrong, right? That I have simply hashed it. But in case you want it, you can unhash it. This is also one more thing. If there is a blank, you can replace it with some kind of constant. Or you can use some kind of a function like minimum, maximum, mean, something. And similarly, you can also look at in terms of a categorical variable. For a categorical variable also, if at all there is a blank, you can replace it with the mode value. So IDX mass is nothing but it is giving me the ID associated with the maximum value. So which is the index that is associated with the maximum value. So you can very well replace it with that same index itself. So you can have multiple ways of handling, right? Whatever we have discussed, I have earlier while discussing about handling missing values, I have brought in some of these. These are all univariate. But we also talked about imputing using a model. Right now, I have not brought in the imputing using the model like KNN imputation or a random forest-based imputation. When we go to the algorithms, I will be discussing about that. So these are some of the things that we have done. Right? So we have replaced anything missing with the minimum value. And probably if at all the mode is required, I will do it. Now, if you really want to see what is the scenario right now, it looks like there are still some more missing values, right? So there are some very high missing values that are there in the data. So you may really want to see whether to drop. So after that, I'm simply saying drop the rows. Now, not necessarily sometimes when you give enough thought to the data, you may really want to replace them with something else. So you may really want to do something more on the data. So I'm not going too much more deeper. All possibilities are good enough. I'm just giving you pointers. It's up to you what all kinds of cleaning you would like to do. Yeah, you can very well assume that both are the same here. I mean, sometimes it's just a kind of typing issue for us. So not an issue. There are a few spaces, especially places, especially when you are dealing with some string related data, right? Probably putting some kind of comments, and there are some spaces, some places where a single index is very much mandatory, right? Especially if you want to put a quote within a quote, etc. So more of text related handling, not in this kind. In this kind, anything will work the same. But if we will fill NA values to some other value, see, I told you there's no argument in all these things, right? I mean, just for the sake of argument, things can go. But sometimes, see, that's again a business case, right? I don't enter a value when, let's say, the value is 0. I assume that it is a 0, so that's the reason I don't enter. Let's say we had a good example which we discussed earlier. So any miscellaneous features, right? Number of miscellaneous features. So if there were no miscellaneous features at all, I just leave it as blank. That means it could very well be that it is a 0. So there could be some cases where data is not mandatorily entered or explicitly entered because they don't find it a kind of a value addition. In those cases, you can very well replace it with a constant. That's an actual business logic. Whereas in some cases, probably it could be a typographic errors and all, but in those cases, never replace them. So replacing is never a good option, right? But if there are cases where replacement is a correct option, then I may have to use this kind of an approach. I hope that makes sense. Then again, because I have dropped some columns, again I am collecting the categorical columns and numerical columns separately, right? Because I have dropped some columns, I'm collecting the categorical and the numerical. Oh, I think I have to drop this. Then I am calculating the categorical and numerical. Now look at your target variable. What is your target variable? The target variable is a categorical variable, right? So what is that you would like to do? You would like to take, because it's a categorical variable, you take one numerical column along with a one categorical column and try to look at the descriptive statistics across the category. So just to understand, right? So just to probably I don't require all of them. I don't require all of them, but I am more and more interested with respect to the target. So which observations, so loan amount, how is it differing across the non-defaulters and defaulters? How is the term differing across? So basically, this is just to get some kind of a distribution across both the defaulters as well as the non-defaulters. Imputation or missing value treatment can alter distribution. Yes. Imputations can very well alter the distribution. So again, so you have not adjusted for the distribution yet, right? You have not converted the data into a non-linear transformation or something like that yet. So the skewness kurtoses can very well change, right? So you may have to relook at them, and based on that, you may have to take the next. So imputation is always a last choice. It's always like either you remove the rows or the column. That's the first better choice, unless the data is having an explicit mistake in it. Okay. We can also take only for the we want that you think it is. I did not get your question, Dev, possibly. So also, if a data set is imbalanced, we need to be more cautious in them. See, generally, the imbalance is more and more to do with my target variable, right? Imbalance with the feature variables. I don't want to consider it that seriously, right? But imbalance with the target variable is more and more important thing, and we have some ways of overcoming that imbalance also. We would be looking at probably when we are solving this problem itself going forward, right? And there are various ways of handling the imbalance. Possibly I have a slightly different approach to look at the imbalance. I'll talk about it. Okay. Then so you have the credit score. So you are looking at all the numerical values just to see what could be the importance. Right now we are not looking at any feature selection or anything, but just trying to get some kind of an broader understanding, right? So there's nothing much here. Similarly, I can also look at which categorical variables could be important and which categorical variables could be unimportant. So from that perspective, I take the categorical card. So basically here in this exercise, my target variable is a categorical variable. So I would look at interactions between a categorical variable and another categorical variable, and a numerical variable. So this is my target and these are my predictor variables. So I am trying to look at for different categorical values of the target, what is the relationship between two categorical variables. So you may be knowing that if I want to look at if there is any kind of independence between the two categorical variables, I can very well look at a kind of a chi-square test, cross tabulation analysis, and along with that I can also step into a chi-square test. Similarly, if I want to do with respect to a numerical variables, I can very well go for a t-test. But I mean, this is just because, but we have very sophisticated mechanisms later on when we are doing the feature, selection kind of mechanism. But here, this is primarily to look at creating a kind of pairs of categorical column. So you could see that the target is paired with all the other categorical columns. So you can see here target versus loan limit, target versus gender, etc. So I really want to see which of the variables are significantly independent and which of them have a kind of a dependence with respect to the variable. Now you could see here target versus the loan limit. Look at the p-value less than 0.05. So this is a chi-square test, p-value associated with the chi-square test of independence. So when we are using a chi-square test of independence, p-value of less than 0.05 means they are not independent. There is some level of dependency between them, which means for our future purpose, we can say loan limit has some kind of a predictive power with respect to the target. Similarly, gender has a predictive power with respect to the target. So basically, it looks like different genders have different proportions of default. Looks like that is what is being communicated by a p-value less than 0.05 here, right? Loan type is also a very important driver towards the target. Loan purpose. So we are seeing a lot of variables. Credit worthiness. Definitely open credit is not there, right? So possibly we could have removed this open credit also. I don't know why we have still kept it. Even this is a univariate, if I'm not wrong now. Business or commercial is very useful variable in predicting the target. So at least we can see that there are a good number of variables, categorical variables, whose p-value is less than 0.05 with respect to the chi-square test. So we can very well say that all these variables could play an important role. The total units may not be an important variable. The credit type may not be an important variable because the p-value is greater than 0.05. So there are a good number of variables which are pretty much important. So which means we can progress further. This just gives you a very high level feel. At least are there a few variables which are impacting variables, which have a which are not completely independent. Are there some pairs at least where the target can be linked to? Otherwise, we can scrap the model here itself. Right? That is the prime reason, just to get a kind of a broader picture. Right? And at the same time, we can also think of doing some kind of a correlation between all numerical variables. Here, numerical variable, our target is not a numerical variable here. So whatever the correlation analysis we are doing, it is between the explanatory variable. It has no link with the target variable. So when you are doing between the feature variables or explanatory variable, we should see that the correlation should be as low as possible. Right? If they are higher, then we have a way of handling them. So in feature selection, I have handled all these scenarios. So we will, but at least this is giving you some picture. Okay, loan amount and property value, they are highly correlated. Right? And probably income and loan amount is also decently correlated. But we have something, property value and loan to value ratio are negatively correlated, and so on. These are some of the higher correlations or lower correlations that we have got. Then we also look at the outliers. I can use a Z-score. I can use a Z-score, and using the Z-score, possibly by putting some kind of right, probably I say any absolute value more than 4, I can take it as an outlier. So directly it could see that in loan amount, I'm seeing there are 18 outliers altogether, going with a Z-score of more than 4. Right? Probably term is not having any outliers, but property value, there are 30 outliers. Income, there are 27 outliers. So right now, I may not be interested in deleting all of them, because once we do a non-linear transform, right? Once we do a non-linear transform like the logarithm or a square root, or a more generalized version called Box-Cox transform, we will see that the number of outliers can automatically come down. So after that exercise, after trying to adjust for the skewness and kurtosis by doing a kind of a relevant non-linear transform, I can very well do this exercise even after that. So right now, I don't want to take a decision based on the outliers right away. But after I do a kind of non-linear transformation on the data, right, then I would like to take care of this outliers. And once we are removing any outlier from the data, you have to scope the model. You have to say that this is the limitation of my model. My model cannot handle property values beyond this. So those are some of the kind of conclusions that you would bring up. But at least this mechanism is identifying that there are a few variables only where there are outliers. Loan to value ratio, there is only one value that is an outlier. But typically the outliers are under income, property value, and loan amount. So there could be another way where you are going with the interquartile range. So here We all know that Q1 minus 1.5 times the interquartile range could be your lower limit. Q1 plus 1.5 times the interquartile range could be your higher limit. But here we are taking 3 times the interquartile range on both sides, which means we are giving some more leeway. So anything that is beyond the upper tail or any value that is below the lower tail, even after doing this much of an adjustment, those things I can call them as outliers. Now, even from that perspective, I could see that this has 15 outliers, but term is having 773 outliers. This is going to be a very too much kind of stuff, right? So probably you may say that in some cases it is not that better. I mean, probably using the interquartile range as a base may not be a good option at all, because it is looking for 773 outliers here, 49 outliers. So right now it's not at all advised to delete. And basically for all the quantitative variables, once I do a kind of a conversion to normality by doing the appropriate transformation, it is always better to check the outlier based on the Z score rather than anything else. So Z score beyond 3.54 something, you can very well treat it as outlier. After you do a non-linear transformation, don't do any kind of a outlier removal at this stage. At this stage, you just try to understand which variables can have some kind of outlier. And in some cases, this is where is the Winsorization thing coming in, wherein I will set some quantile by default. I will set some quantile by default. The lowest 0.5% of the data or the highest 0.5% of the data will be directly treated as outliers, even though they are outliers or they are not outliers. Sometimes we say, I will by default, I automate that process saying the lower 0.5% or the upper 0.5% of the data will be treated as outlier. So every column will have outliers in that case, right? So this is not preferred in all the cases. There are specific applications, especially if you say that your data can have noise because of various things, especially the financial markets related data, etc. Then to build an appropriate model, you say rather than going through the data in more detail, you'll say that I'll remove the bottom 5% of the observations, and I'll remove the top 5% observations of every stock, and I will try to build a model for the remaining 99% of the observations only. So that is where you are going for a Winsorization kind of a mechanism. Now, if you are going with Winsorization, so obviously 1% of your observations will typically come out, because the bottom 0.5% and the top 0.5%. So approximately you could see that depending on the values, 39, 36, 42, 36. So those are the number of outliers that are there in your data. So every column is having some kind of outliers if you are going with the Winsorization mechanism. Then the fourth mechanism for going ahead with the outliers is a ZR score, which we have already talked about earlier. So this one is a range-based outlier. So while the normal outlier, when you are going with a Z score base, we are simply saying X minus mu by sigma. Whereas the range-based Z score is nothing but X minus median by mean absolute deviation, right? The median divided by the mean absolute. So you are going with the mean absolute deviation. You're getting a median absolute deviation, so this should be just MA. This should be just MA. And this is multiplied by a constant 0.6745. So if this value is greater than 4, you can call those as outliers. Now going by this approach, we could still see that possibly we are seeing a lot of outliers even here. So even here it is showing that in terms of term, almost 773 outliers have typically come up. Whereas for some of the variables, there is only one outlier, and for some of the variables, there is no outlier. But at least overall, the picture is telling me that the outliers for some of the columns are very, very large. And obviously, I know that the skewness and kurtosis for those values is much higher. So if I can try to address that skewness and kurtosis by doing some kind of non-linear transformations, it might very well be possible that the number of outliers will come down drastically. And once the number of outliers comes down, I can very well remove those outliers. In that case, it would not be a big loss of data, right? So that is what is the intention. So right now you can very well, now I have also put multivariate outliers also, but right now I will not run this. Multivariate outliers, this is DB scan is typically your clustering algorithm. So when we discuss about the clustering, I'll talk about the DB scan algorithm. I'll explain the density based clustering. So DB scan is nothing but density based clustering. So we would be talking about it, and then as an application, I'll tell you how it can help you in identifying the multivariate outliers, right? Similarly, for each of them, so it looks like in this case, so just to give you an input, when a DB scan is run, wherever you get a -1, right, in the algorithm, wherever you get a -1, then you will say that it is those are the outliers. So basically here, with respect to income, there are 315 outliers. Yeah. So Paras, you are right. Yeah, this is a density based clustering algorithm. So we would be working out with that, and we'll see that some of them, so wherever, just to interpret, just for running and interpreting, wherever you get a -1, so you can say that in LTV, there are 11 outliers. So you can very well say wherever the -1 category has come, that can be treated as outliers. Similarly, I can also use a random forest based concept called isolation forest. So this is also something which we will be doing later on. So here you could see that any -1 is like an outlier, but this one identifies too many outliers. So we have to be very careful when we are executing these kind of algorithms, because too much of data is typically being identified as outliers, right? Then you would also go ahead doing different kinds of visualizations. I don't want to, you can practice them out, right? We have discussed about the visualization, so I'll not execute the visualizations now. I hope, I mean, you can, because I'll share this code with you, you will be able to run. We have discussed all these visualizations earlier when we talked about CBOR. So I have plotted different visualizations to understand the distribution of the data, whether the data is having any kind of outliers in it or not, pairwise outliers, then probably looking at the normality of the data by using the QQ plot. So we have plotted all the various things. Okay. then I'm actually coming on. So until here, anyone has any kind of queries, let me just handle them. Otherwise, I want to move forward. Right, we are trying to go with the solution. So that is where I really want to finish off all the pre-processing if possible today, so that the actual model building can start from the tomorrow's session. So if there are any questions, I'll just pause for a few minutes, but I would like to look at a few more things as well. Okay. All right. So then I'll move on to the next one. Okay. Now we are going to get into the pre-processing aspects. Okay, you just talk about one test for checking normalization. Normalization or normality? Normal distribution. Yeah, so in the beginning we looked at the Jark-Bera test, right? In the descriptive statistics, you got the Jark-Bera test. That is the test of normality. Though there are various other tests that are available, but the Jark-Bera test is one thing that you get in the descriptive statistics. That is based on the skewness and kurtosis. So the null hypothesis for this test is the data comes from a normal distribution. The alternate hypothesis is the data does not come from a normal distribution. So you can very well check the p-value of this test. If the p-value of the test is less than 0.05, you can very well say that the null hypothesis gets rejected and the data does not come from a normal distribution. But if the p-value is greater than 0.05, you can very well, you will not reject the null hypothesis and you can make an assumption that the data comes from a normal distribution. Would that suffice? Or you can very well go with looking at the QQ plot that we have plotted towards the end. That is a kind of a visual way. A QQ plot also can give you the normal distribution of the data, right? So probably you can very well see. So if at all the data follows a normal distribution, the point should be along this red line. So if the points are well deviating from the red line, generally the deviations will be towards the lower side and the upper side. So if the points are well deviating on both the sides, then you can very well say that the data is highly deviating from a normal distribution. So probably in all the cases, we are seeing that the data is very much deviating from a normal distribution, including the credit score, right? And probably this is to some extent, it looks like loan to value ratio, except for this one outlier. But overall, it looks like a decent fit to the normality. Then debt to income ratio also to some extent. Okay. Then the next thing that we are going to look at is, now we are taking the data more closer towards the modeling aspect, right? So I will be performing a few things. One is splitting the data into training and testing. We talked about it, right? So there is a these are all for validation purposes. So we will have to validate. So that's the reason we will build our model on one training data, and we will validate, or we will evaluate the model on a testing data. So that's the reason randomly we will split the data into a training data and a testing data. We would be scaling the data. We also talked about this. We said probably there is a standard scaler, which is like all the columns will be converted into their set scores, or they would be converted into a range between 0 to 1. So these are all different kinds of max. So there could be a, this is like a Z score scaling. This is like a min max kind of a scaling, or we'll have max absolute scaling. Like that, we have a couple of scaling mechanisms. And these are some of the transformation mechanisms, non-linear transformation. We talked about the non-linear transformations like square root, log, etc. Now, the parent transform to all these log, square root, etc. is the power transform, right? So power transform, so basically you will find power transform is like a generalized transform, of which the square root, all these transforms are the special cases of the power transform. So we will be doing those things. So this will try to address the normality in the data. And as a part of feature selection, we would also be looking at some of the columns, if at all. Now, if you remember, we have removed some of the columns with single variance, with zero variance. But there might be some which would have again cropped up into the data because of some other transactions that we have done on the data. So either fully zero variance or very near to zero variance kind of things also I may want to remove from my data. So that is where I'm setting some kind of a variance threshold. So these are all the things that we can directly work with the scikit-learn. Scikit-learn is a kind of a library for all your machine learning related activities. So we would be working out on the various. Now from here onwards, we are working completely on the various modules of scikit-learn. Now, if at all, right now, so here, if at all I have some names, the reason why I use this is, if at all I have some names for my target variable, like no, yes, something, better replace them with a 0 and a 1. In case here we have 0 and a 1 only, but because I wanted, again, it's not mandatory, but probably that would make things more easier at a later point. So the event which we are interested in predicting, let that be 1. Whichever is the event. Now here I want to predict default. Non-default is not a kind of an event for me. Default is a kind of an important event for me. So I would be more interested in modeling the default. So if I have to model the default, I can say that 1 is given to that yes, and 0 is given to that no. So that is one additional step that we are doing. Then separate the feature variables from the target variable. So your target is that target column. So put that as Y. Take that target column as Y. And except that target column, all others. So you are dropping that target column and you are calling that as X. All the other data except the Target is typically treated as X and the target is treated as Y. Now again from this list, because you have been dropping at the various columns at various intervals, I am taking again the list of categorical columns from S and list of numerical columns. Now here there is an important thing that we have to do. This is where your encoding, categorical variable encoding is coming up. We talked about different ways of categorical variable encoding, right? One is a simple, you are doing a kind of ordinal encoding. This is more preferred if we are having ordinal data. Let us see if there is any ordinal data in our case. Otherwise, it would always be better to go ahead with the dummy variable encoding, which is otherwise called as one-hot encoding. So before I do a one-hot encoding, because here I have done a one-hot encoding altogether, but let me just see if there is any categorical variable in the data, which is an ordinal variable, so that I would prefer to do an ordinal encoding rather than a one-hot encoding, right? Loan limit, gender, type loan. So I don't see any increasing or decreasing kind of variable. Yes or no kind of variables. Let's see in the descriptive statistics. Yeah, this is what can help me. Type 1, type 2 may not be any increasing or decreasing. Loan purpose also P1, P2, P3 may not have any kind of an order. Credit worthiness, I don't know whether, there are only two categories. Two categories you don't need to bother. Only if there are three or more, and if there is some kind of an increasing or a decreasing order, then we can very well treat it as occupancy type, not necessary. Total units, we don't know. One unit, 2 unit, and greater than 2 units. So in that case, I can very well think of doing a kind of ordinal encoding, right? So I can very well think of doing an ordinal encoding there. But apart from that, I don't think we require any ordinal encodings anywhere else. Right? Only the order matters only in that case. So I can even go ahead doing the dummy variable encoding for all of them also, including that one. But otherwise, you may have to replace those values with 1, 2, 3 kind of stuff. And so which means you will otherwise I'll do that also, so that you will have a comfort of all combination. So I would do here. Let me do an ordinal encoding. Okay. So before we do this, right? So first we need to import. Let me just look at. Okay, so I'll first copy this. Okay, so let me put this ordinal encoding. Then I would put the fitter. I can directly do a fit transform. Right, I'll do a fit transform. So here I'll have to give total units, right? Yeah, this is what I'll give. I do this fit transform, and probably I will save it into the same location. I'll save it to the same location. So which means I'll overwrite it. So this is what we are doing as a part of ordinal variable encoding. So whichever variables we want to do a kind of ordinal variable encoding, we can do that. I want to do it only for this column. Just give me a minute. I'm trying to figure it out. Or sometimes it would be better to directly. I mean, I'm somewhere losing it out. So Okay, otherwise I'll get back to you on this part. Let me work it out separately because I think it is giving me expected 2D array got 1D array. Array is having only one U. All right, so let me look at this part. Right, for time being, I'm just holding on. Probably I'll come out with this. I'll come out with the uh, ordinal encoding. Yeah, you need two access for the transform. That's what I'm trying to. So I take I don't. But if I'm doing it on the total access, so either this is a series object. Then I need to do it on the entire data otherwise, but I want it only on one column. Otherwise, I have to convert this into a kind of a data frame or so if I have to convert. So yeah, I'll look at it and I'll come back on that. Right. So the next thing, okay, let me just look at the other queries. Probably we can Google it out. We can get ordinal encoding. I'm just looking at the example out here. Okay, if there are 5 features with 2 categorical and 3 numerical variables, how to find the least variance feature? Least variance feature. So what is this least variance feature? How to find the least variance feature? So you meant to say normally a variance is associated with the standard deviation. So in case of numerical variables, you can directly use standard deviation. But in case of categorical, probably you may have to go ahead with an assumption of a binary distribution, binomial distribution, or something like that. I didn't get your question completely. What would be the method to find the least variance feature? That is what I'm trying to understand. Or you do a kind of dummy variable transformation and look at the variance of each of the variables. Among these 5 features, which one is the least feature? Least feature is least importance, or what do you least? I didn't get what is this least. Least variance. So in case of a numerical data, you have your standard deviation that talks about the variance. Whereas in case of categorical, then probably you may have to look at p times 1 minus p kind of a thing, which could be a measure of the variance, especially if there is a binary data. Okay. But yeah, probably I need a better clarity on the question. Okay, then I'll move on to the next one. In the next one, I am creating a dummy variables for all the columns. For all the categorical columns, I am creating dummy variables. So this dummy I am directly using from the pandas. I am not using from scikit-learn, right? Probably because I mean there's a lot of comfort in working with in the pandas, especially for dummy variable creation. So I'm taking the entire training data. Then whatever are the column names, we have already collected all the categorical columns. So you are trying to put an underscore after that name of the categorical column, and all the values associated with the categorical columns is what are the new headings that you are going to get. So you see this, the dummy variables that got created. What happened? So the dummy variables that got created, yeah. So these are the dummy variables that got created. Let us see the names that have come out as a part of the dummy variables. Okay, so these are the initially these are all the numerical columns, they are as it is. But look at it, loan limit underscore NCF, gender underscore joint, gender underscore male, gender underscore sex not available. Because what we have said, in case of the encoding, one hot encoding or the dummy variable encoding, one observation will, one category will be left out. Generally here when I said drop first equal to true, the first category will get left out. So we had female, male, joint and gender not, sex not available. So that's the reason female is omitted, and the remaining three categories are converted into 3 columns of the data. Then similarly, you can look at for all the other approval in advance, loan type 2, loan type 3, because loan type 1 is going as a part of the default, as a part of the intercept. Loan purpose, P2, P3, P1 is taken as a part of the intercept. So like that, you have so many new columns that are being created. Ages also. So you could see that 35 to 44, 45 to 54, and so on. So we have seen this are so the data got transformed into all numerical data only, even though there are so many categorical variables in your data, that entire data got converted into a numerical data now. So this is one important step, because majority of the models can work only with the numerical data. So this is one more aspect that you can very well look at, right? So after you have taken the data, so the pre-processing is like you separate the target variables and the feature variables. Then you look at creating a dummy variable, creating all the dummy variables out of the data. Then you split the data into training data and the testing data. The next step, you split the data into the training data and the testing data. So approximately you can specify either 30% or 25% or something, that is your testing set, and you split the data into training and testing. So obviously this train test split function actually creates 4 subsets. One is called as a X train, training of training data relating to the feature variables, training testing testing data relating to the feature variables, training data with respect to the target variable, and testing data with respect to the target variable. Then you can very well we can also capture the names of the columns also, because we would be utilizing those column names at different points in time. So because sometimes when I delete some of the columns now as a part of feature selection, there are so many such kind of activities that we are going to do. So whenever you are deleting some column, even the column names also need to be updated. So that's the reason I am creating some variable which can capture the column name. I don't need to look at the training data and testing data separately. We know that there is a, so now if I look at the testing data, these are the columns these are the observations that came into the testing data. We said approximately 1500, right? 30% means approximately 1500. So these are the index numbers that are a part of the testing data, and the remaining index numbers will be a part of my training data. Then this is where we are implementing different feature selection mechanisms on our data. So what we will do is, I think features, of course, some of the feature selections we have already discussed. One is that constant features removal. So we might have already removed them by now. But if at all, due to some of the modifications that we have done, if any feature comes out with a zero variance, means only single unique value because of doing some kind of because of doing some kind of dummy variable creations, or because of some other reason, if we had ignored the removal earlier of some of the zero variance features, I can very well use this function called variance threshold and set the threshold value as 0, which means it's a zero variance removal. And I would directly fit this to my entire X-train data. There I was trying to fit. So yeah. So here I'm trying to fit to the X-train data, the complete training data set. Right. So if I really want to do it for only one column, I'll have to just see that. So here we are fitting and transforming. We are doing it to the entire training data. So that constant filter, I'm setting a variance threshold of 0, and I'm trying to fit that for the entire data. So once I fit this, right? So this one probably I don't need every time. So I want to see how many columns are there that are getting the support. Getting the support means the constant filter is applied, and that variable is not to be deleted kind of a variable. So there are 39 variables that are getting the support, which means 39 variables would not be deleted. So you could clearly see here. So I'm looking at the list where those variables are staying. They are not getting deleted. So they are in filter.support. So all those variables which are not to be lost. So I'm seeing that they are all false, false, false. So wherever there is a true, that variable would be removed. So we are getting support wise, it should be the opposite. So whichever variables are true, they will not be removed. So all the variables are true. So which means the column names wise also, all those columns will be retained, and which means my data now is updated. So right now with this variance filter, variance threshold, the zero variance filter, nothing, no rows or no columns are removed, because no column is a zero variance column. So still our data typically is lying like, or I should have simply said head. So we have all the columns retained after this step. So zero variance threshold is one observation that you would always like to work upon. Probably let me do a head rather than doing this entire thing. Right? So we have all the columns being retained. So which means we'll now move to the second mechanism, which is otherwise called as a near zero variance or a quasi constant removal. So generally, what is the way you can very well look at is, so even if you are saying that there are only two categories, as I told you earlier, let's say 0.1% of one category and 99.9% of the other category, right? The variance for such a kind of category would be nothing but 0.001 multiplied by 0.999 p times 1 minus p. So which can very well become 0.000999. So it can also be rounded up to saying 0.001 or something. So if I can say that 0.001 is a kind of a threshold that I'm going to set, right? Any observation, any column which is having a variance threshold of 0.001, which means 0.1% of the observations in one category, one having one value, and all the remaining 99.9% of the observations having another value. In that case, the variance of that particular column would typically come out as around 0.001. So I can set some such kind of a threshold, and in some cases, if I want a little bit of more columns also, more observation, then better set it to 0.005 or something like that. Let's say if I'm setting to 0.005, right? So if I'm setting to 0.005, I can very well fit this quasi filter to my entire data. Now I can very well see how many are getting the support. Now I could see that the support is 38 only, which means one column would have got eliminated now. Earlier we got a support for 39. So that particular column would have got eliminated, right? We can very well check which column got eliminated. Possibly you can use a similar kind of mechanism. We can use a similar kind of mechanism to check which of them have got that support. We can very well check which of them has got that support. So you could see that this column is the one that is going to be losing out. You can very well check which is that particular column, and you would remove that particular column from the data. And you would also give the now your column names also will contain. So basically I'll update my column names also accordingly. I'll have to update my column names also accordingly. Now you are Oh, column names are already updated. I'm sorry. Here the column names are already updated. So that's the reason I was getting the error. So I don't need to update the column names again because the column names have already taken care of that line of code. So from there, I can very well get my new data. So which means one column would have got deleted now. Now my data got into 38 columns now. Instead of 39 columns, my data became only 38 columns. So one column got deleted because of that quasi-zero variance kind of thing. But of course, here you should, I have directly written that, so possibly if I wanted to know which column, then before this step itself, so whichever are the false columns, I should have captured those false columns also to understand which which variable has got deleted, right? Probably one of those dummy variable encoded variable has got deleted because probably the coefficient, so some category would have occurred, very minimal number of uh, observation. So because of that, it would have typically lost out in the total list. Right now, this is the overall data now. So we are actually filtering out at every stage, and we want to take the data in such a way that only the most important variables would be retained for the next modeling process. All right, I'll stop it here. Possibly I'll share this entire file with you. Right, this is the kind of end-to-end process that I'm trying to capture, so that in case you want to work it out with some other data set also, it gives you a lot more comfort in practicing. And based on that, we can even discuss out any specific practical related issues as well. All right. So in case you have some queries, I will try to discuss them. Otherwise, I think we